In this video, we will study from exercise 6.8 from vector algebra. Now, the condition for a line to lie in a plane. So, you have a plane and you have a line. So, we will see what is the condition that this line can be in this plane. So, we observe that the straight line will lie in the plane if every point on the line lie in the plane and the normal to the line to the plane is perpendicular to the line. So, two things that we will study is that one, that every point on this line lies on the plane and the normal to the plane, which will be perpendicular to the plane, will be also perpendicular to the given line. So, if our line is given by this formula, the line here is given by R vector is equal to A plus TB vector. You know that B vector is a vector parallel to this line and A is the position vector of a point A on this line. So, if the line R is equal to A plus TB vector lies in the plane R into N vector is equal to D. So, again you know this, that R is the vector position vector of any point on the plane and N is the normal to the plane and D is the distance of the plane from the origin, and A dot product with the N is equal to D. So, this is the condition that we have to, if this is the plane and this is the line, then the condition is A dot product with N vector is equal to D and B dot product with N vector is equal to 0. Also, if you are given the Cartesian equation form of the line and the plane Cartesian equation form, then, and let's say this is our Cartesian line and this is our Cartesian of the plane, equation of the plane, then the condition that it should satisfy is that A, which is the coefficient of x here, into x1, which is the point on the line, plus B y1 plus C z1 plus D, which is on the plane, the D here is equal to 0, and also AA plus BB plus CC will be equal to 0. So, these are the two conditions that it should satisfy. These are derived from these two conditions here. Next, let's look at an example. So, the question says, verify whether the line x minus 3 by minus 4 is equal to y minus 4 by minus 7 is equal to z plus 3 by 12 lies in the plane 5x minus y plus z is equal to 8. So, this is the line and you need to verify it lies on this plane. So, what is our condition, or rather let's first point out all the points here. Our x1, y1, z1 will be the point on the line which is 3, 4 and minus 3, and the direction ratios of the straight line are given by minus 4, minus 7 and 12. So, you have it here, and the direction ratios of the normal to the given plane, which is this plane, is given by capital A, B, C, that will be coefficients of x, y and z, which is 5, minus 1 and 1. Okay. So, we have this, our x1, y1, z1 is equal to 3, 4, minus 3, and it satisfies the plane 5x minus y plus z is equal to 8, which means if you put this point 3, 4 and minus 3 onto this plane. So, if you say 3 times 5 minus 4 plus, sorry, it will be minus 3 here, minus 3 will be 15 minus 4 minus 3, which is equal to 8. So, it satisfies the given plane, which means this point is on this plane. And next, let's bring out our condition, which is AA plus BB plus CC should be equal to 0. So, if you put the values of AA, BB and CC here, your A is minus 4, B is minus 7 and C is 12, and your capital A, B, C are 5, minus 1 and 1. So, substituting those values here, you get the answer as minus 1 and it is not equal to 0. Therefore, the normal to the plane is not perpendicular to the line, hence the line, given line does not lie in the plane. So that's the answer for this example. Next, let's look at the condition for coplanarity of two lines. Okay, so you're given two lines here. These are the two lines, and the line passes through the point A, L1. Let's call this as L1. It passes through the point A, and L2 passes through the point C. And A is the position vector of the point A, and C is the position vector of point C. Now let us consider vector B, which is parallel to L1, and vector D, which is parallel to the line L2. Then we know that B cross product with D will be perpendicular to the given plane. Okay, so the lines can be now, since we have already described what is B vector, what is C vector, and what is D vector, A vector, we can rewrite the lines L1 and L2 as R is equal to A plus SB plus R vector is equal to C plus TD vector, and they are coplanar. Okay, so they lie in a single plane. Then let A and C be the points whose position vectors are A and C, which we already saw here. Then A and C lie in the plane. So then A and C should also be on the given plane. Since B and D are parallel to the plane, B cross product with D is perpendicular to the plane. I explained this already to you. So AC vector is perpendicular to a B cross product with D vector, which is your AC vector here, which is on the plane, will be perpendicular to B cross product with D. So if you have a dot product of AC and B cross product with D, then that will be equal to 0. So that's what we are doing here. AC is nothing but C minus A vector, and dot product with B cross product with D vector is equal to 0. So this is the required condition for coplanarity of two lines in vector form. So if the lines are in the Cartesian form, then let's say this is our line 1 and this is our line 2. They are coplanar if x2, which is a point on the line 2, minus x1, which is the point on the line 1. So that's your first row of the determinant, x2 minus x1, y2 minus y1, z2 minus z1. Then we know that b1, b2, b3 are coefficients of a vector that is parallel to this line, or they are also the direction ratios. Similarly, d1, d2, d3 are the direction ratios of the second line. So this determinant of x2 minus x1, y2 minus y1, z2 minus z1, b1, b2, b3, d1, d2, d3 is equal to 0 is the condition required. This is derived from our parametric form. So that's the condition for coplanarity of two lines in Cartesian form. Next, to find the equation of a plane containing two non-parallel coplanar lines. So we have two lines which are not parallel, but they are coplanar. They are in the same plane. So you are given two lines in the same plane, but they are not coplanar. So if I'm going to draw, or if I'm going to explain the line 1 here, we can actually mark this as our line 1 and this as line 2, and so this will be your line 1 and this will be your line 2. So the equation of these lines are given here. So let L1 and L2 be two non-parallel coplanar lines. Then B cross product with D is not equal to 0. Now we know that these two are not parallel. Therefore, the cross product of this will be not equal to 0 vector, because B and D are parallel to L1 and L2. So their cross product will not be equal to 0 vector because they are not parallel. Then let P be any point on the plane. So we are going to consider P as any point on the plane. So let P be any point on the plane, and let R not vector be its position vector. So R naught vector is the position vector of the point P. Then the vectors are minus A vector, R vector minus A vector, then B vector, D vector, as well as R naught minus C vector, which is a point on the line 2. B vector and D vector are also coplanar. All of these will be coplanar. So we get R minus A vector is equal to TB vector plus SD vector. This is using our vector equation, not vector equation, using the equation of the line. Or it can also be R naught vector minus C vector is equal to TB vector plus SD vector. So we can either use a point from the line 1, or you can use the point from the line 2, and using our B and D vector we can derive these two equations. Therefore, the vector equation in the parametric form, rearranging these two, would be R is equal to, taking the A to the other side, A plus TB vector plus SD vector, R is equal to C vector plus TB vector plus SD vector. So here our T and S are scalar quantities. Now for the non-parametric form of the vector equation. So we will consider the same lines L1, L2 with vector A, B, C, D as in the previous case. So we will also prove that B cross product with D is not equal to 0. Then let P be any point on the plane and R vector be its position vector. Then, as we have seen in the earlier case, that these vectors are all coplanar. So our non-parametric form of the vector equation will be given by this formula, which is R naught vector minus A vector dot product with B cross product with D vector is equal to 0, or you can take the point from the second one and you can derive this. Therefore, this is the non-parametric form of the equation, vector equation. Extending our results to the Cartesian form of the equation. So this is our line 1 and this is our line 2, which lie on the same plane. So our direction ratios of the line 1 is B1, B2, B3, and the DRs of the line 2 is D1, D2, D3, and the point x1, y1, z1 is on the line 1, and x2, y2, z2 is on the point 2. So extending our result, we can say it's the determinant x minus x1, y minus y1, z minus z1, b1, b2, b3, d1, d2, d3 is equal to 0 is the condition, or is the equation of the Cartesian equation of the plane. So it can also be using the point x2, y2 and z2, replacing instead of x1, y1 and z1 equal to 0 is also the equation of the plane. Example 6.46. Show that the lines R is equal to given by this equation and R is equal to given by this equation are coplanar. Also find the non-parametric form of vector equation of the plane containing these lines. So we can rearrange this as R is equal to A plus TB vector and R is equal to C plus SD vector. So our A vector will be equal to minus 1, minus 3 and minus 5 k cap, which is this, and our B vector will be given by 3i cap plus 5j cap plus 7 k cap, and our vector C will be 2i cap plus 4j cap plus 6 k cap, and our vector D will be I cap plus 4j cap plus 7 k cap. Now the condition for the two lines to be coplanar is that C minus A vector dot product with B cross product with D is equal to 0. So let's substitute the values. So D cross product with B cross product with D vector will be determinant of I cap, j cap, k cap, B1, B2, B3 are 3, 5 and 7. So 3, 5, 7 and it's 1, 4 and 7 here, which is equal to, for the simplifying this, you will find the answer as 7i cap minus 14j cap plus 7k cap. And our C minus A vector is 2 minus of minus 1, which is 3i cap. Similarly then plus 7j cap plus 11k cap. So we have these two. So let's substitute this value and this value into this. So we get, substituting, the result of this is equal to 0. So I can try and quickly show this for you. 3 times 7 is 21. 7 times 14 is minus 98. And what is 11 times 7 is 77, which will be equal to 98 minus 98, which is equal to 0. So it's equal to 0. Therefore, the two given lines are coplanar. Then let's find the non-parametric form of vector equation of the plane containing the two given coplanar lines. And we know that the plane containing the two coplanar lines is given by this formulae. So R minus A vector dot product with B cross product with D is equal to 0. So substituting for A, B and D, we get R minus of, substituting for A vector here, minus I cap minus 3j cap minus 5k cap dot product with, substituting for B vector here, 7i cap, sorry, B cross product with di cap, D vector, which is this here, which is 7i cap minus 14j cap plus 7k cap. So that's what we have here, is equal to 0. Thus the required non-parametric vector equation of the plane can be described as R into I vector minus 2j cap plus k cap. This is because our A vector dot product with B cross product with D will be equal to 0.
Thank you for watching Maths Tutorial Anand. Please like and you can comment if you have any questions, and do not forget to subscribe to get more videos like this.